All right, let's go ahead and review this Chapter 6 study guide. Now, you're going to need to stop and pause the video and fill in anything that it might be missing for you, okay, as I go along, because I've already typed this in, okay? So the first section has to do with the Earth. So the rotation axis is an imaginary line on which the object rotates. So we know that that is like so, okay? So we have our Earth, and then we have this axis from pole to pole. It's an imaginary line. So rotation is a spinning motion. So the length of the rotation is 24 hours, which gives us our day and night. So revolution is the motion of one object around the other. One object around the other. So the length of our revolution around the sun is 365.25 days, 1 year. So that quarter day is what adds up, and every 4 years we have a leap year. So the direction is counterclockwise, counterclockwise. So the rotation direction is west to east, so the objects in the sky appear to move east to west. So if you need to stop and pause this video so that you get this Earth section done, please do so. So we're going to go on to the moon section. The moon. Why do we see the moon? Sunlight reflects off the moon. The moon does not make its own light. It is a solid object. So Earth does not make its own light. The planets do not make their own light. Only a star can make its own light through nuclear fusion, right? And so that is our sun. So we see the moon because the sunlight reflects off it. Does it emit light? Nope, never does it emit light. Only reflects. Only reflects the sun's light, okay? All right, so its length of rotation, so that would be once on its axis, is 27.3 days. So the moon rotates once on its axis in the same amount of time that it takes to revolve around Earth. Because if we look at our length of revolution, it's the same. It is also 27.3. This is called synchronous rotation. This is why we always see the same side of the moon. So you need to put a big old star by that and make sure you stop and add this to your notes, that it rotates once on its axis in the same amount of time that it takes to revolve once around Earth. So we always see the same side of the moon, which is called synchronous rotation. So the moon revolves around the Earth. The structures on the moon, so we have maria, which are those large, dark, flat areas on the moon. How are they formed? They were formed when lava flowed up through moon's crust and solidified. Craters were formed by impacts from objects in space, meteors, meteorite, those types of things, asteroids, planets with small space rocks in the solar system banging into the moon cause these craters. And then the maria is the lava flowing up through the surface of the moon and filling in a lot of those craters. So we have tides. So the definition is the daily rise and fall of sea level. Daily rise and fall of sea level. Spring, we have sun and moon's gravitational force combine to produce the highest high tides and the lowest low tides. The moon phase would be our new or full moon. So remember, how I want you to remember this is spring. It has everything to do with S's. Spring, straight, supersized. So we have the sun and the moon and the earth. That would be the position for a new moon. And then we have the sun and the earth and the moon. That would be the position for a full moon. But bottom line, they are all in a straight line with each other. That is a spring tide. So then our next tide is a neap tide. So the sun, the earth, and the moon form right angles, and the gravitational force is reduced. With the neap tide, we're going to have the lowest high tides and the highest low tides. So they're kind of offsetting each other. They offset each other. So the gravitational pull is not going to be as much. So we're going to have lower high tides, leaving behind more water here for our low tides. So we're going to have lower high tides and higher low tides. And this occurs during the first and third quarter. And how we're going to remember that is neap with our ends, neap 90. Not so high, or not so much. Okay, so when the sun and the moon are at right angles to the earth, those gravitational force, they compete, they diminish each other, they offset each other a bit, and so the high tides are not going to be as high, leaving behind more water for the low tides. Okay, so the force mainly responsible is moon's gravity. So this falls under the idea that there are two forces that affect gravitational force, mass and distance between objects. And so it is the distance. The moon is much closer to us than the sun, and so its force is about twice as much as the sun. All right, so this finishes the first page. Make sure you are stopping as you need to. Okay, so then we're going to get in with solstices, equinoxes, and seasons. So you label the diagram here. So this is how I do something like this. The very first thing I look for is this one that is tilted away. That is actually the easiest one for me to pick up because I can see that that is tilted away. So I know when it's tilted away that that's going to be winter. And so then 6 months later, we know that this one is tilted toward, and that's going to be summer. So then I have to think, let me write the word tilted in here. Tilted toward the sun. This is tilted away from the sun, tilted toward. So then as we make our counterclockwise, we go from winter to spring. So this here is halfway. We're not leaning, we're just riding the equator is riding right alongside that. We're not tilted toward nor away. So our spring equinox, and then we continue to our summer solstice, and then we continue to our autumnal or our fall equinox, where the equator is riding right along that orbit like so, tilted neither toward nor away. So a solstice is a day when Earth's rotation axis is most toward or most away. So in this case here, I've already used purple. In this case here, we are most toward. So this is our summer solstice. Here we are most away. So this is our winter solstice. How do the lengths of day contrast for the summer solstice and the winter solstice? So during a summer solstice, that is going to be the longest day of the year, and the sun appears highest in the sky. So we're going to have maybe about 16 hours or so of daylight. Hours, really nice long summer day, maybe 9:30 or so. It's going to stay light until now. But the winter solstice, we've only got ourselves about 8 or 9 hours of daylight. And we remember back in December when it would be pitch dark, like at 5 o'clock at night, right? And we know that that is not happening over here at the summer solstice. It is not pitch dark at 5 o'clock at night. It doesn't get dark till like 9:30 or so in the summertime. So on the winter solstice is our shortest daylight hour day, and then our summer solstice is our longest daylight day. And so it's going to appear lowest in the sky, because it's so tilted away. So an equinox. So a day when Earth's rotation axis is leaning along Earth's orbit, neither toward nor away. So we've got those right here, and right here. So So how do the lengths of daylight hours and nighttime hours everywhere on Earth compare on an equinox? Well, they're equal. We see the word equal in there with equal, equinox, right? Got that same little prefix here. That's how we're going to remember that we have 12 hours of both. Day and night are equal. We're actually approaching that here on our March 20th, 21st. This year it will be on the 21st. Okay, so that is the equinox. So what are the two forces responsible for keeping Earth in motion around the sun? Gravity and inertia. So inertia, once in motion, stays in motion. And then gravity is keeping us, so inertia keeps us moving. And gravity prevents us from moving in a straight line out into interstellar space. So the two factors that affect gravity are mass and distance between objects. That's what affects gravity. Okay, the two motions of the Earth and what do they cause? Now, this is going to be an area where I have summarized what we did in this first part here into one nice question, okay? So what are the two motions? Well, we've got rotation, once around on its axis every 24 hours, causing day and night, and revolution moves along orbit around sun every 365 and a quarter days, causing a year. Okay, so make sure that you are able to talk about the two motions of the Earth, rotation and revolution, what they do, what they cause, okay? All right, so how does the tilt of Earth on its rotation axis relate to the change of seasons? Hint, the temperature on any area of Earth's surface depends on the amount of energy it receives from the sun. The tilt of Earth's axis combined with Earth's motion around the sun is what causes the seasons to occur. So it is the tilt of Earth's axis. That is what is the reason for the season. If we didn't have a tilt of an axis, then we would have the same season all year round. So it's the tilt of Earth's axis combined with the Earth's motion around the sun is what causes the seasons to change. When tilted toward the sun, that hemisphere receives more direct sunlight, resulting in longer days, shorter nights, and warmer temperatures. Sunlight hits the equator directly and becomes spread out as you move away from the equator. So if we look at our picture here, so right here we are tilted towards, so this is going to be on this half here, we're going to be tilting more towards the sun. So we're going to be moving from like the vernal equinox to the summer solstice. We're going to be getting warmer, and then as we come around this direction, we're going to be becoming cooler. So as we are tilted toward the sun, then we're going to be receiving a lot more direct sunlight. We like that. The days are longer, the shorter nights, warmer temperatures. Sunlight hits the equator directly and becomes more spread out as you move away from the equator. The regions at the poles are colder because they receive less energy than regions near the equator. That's why areas right along the equator, the tropics, the Caribbean, that's why it's always nice and warm, because it's always receiving that direct sunlight, whether the Earth is tilted toward or away. It's kind of neutral zone. So remember, the northern hemisphere and the southern hemisphere have opposite seasons. If it is summer in the northern hemisphere, it is winter in the southern hemisphere. If it is spring in the southern, it is fall in the northern. So make sure that you understand that those are opposite. All right, so we're going to talk about eclipses. So draw the position of the sun and the earth and the moon in a solar eclipse. Include the umbra and penumbra. So we have our sun and our moon and our earth. And the moon is casting a shadow on the earth. In a solar eclipse, the moon moves between the sun and the earth, casting a shadow on the earth. A solar eclipse occurs only during the new moon phase of the moon. The longest solar eclipse lasts about 7 minutes. A total solar eclipse can only be seen by people within the umbra. We know that the umbra is the darkest part of that shadow. So if you have got to be in that little umbra, now it's going to be a really little umbra because the moon is such small object compared to Earth. So you've got to be in that umbra for it to be a total solar eclipse. If you are in the penumbra, which is the lighter then part of the shadow, then you are going to only be in a partial solar eclipse. So then here we go with the lunar eclipse. So we're going to draw the position of the sun and the earth and the moon in a lunar eclipse. So we have our sun. We always have our sun there. That sun doesn't change position. It's just who is in the middle casting a shadow. So it's sun, earth, moon. In a lunar eclipse, the moon moves between the sun and in the lunar eclipse, the earth, moves between the sun and the moon, casting a shadow on the moon. A lunar eclipse only occurs during the full moon phase of the moon. You can still see the moon during a total lunar eclipse because Earth's atmosphere is going to deflect some sunlight into the Earth's umbra. And it's going to appear kind of an orangey color, okay? This is going to be what a lunar eclipse looks like. Lunar eclipses don't occur every month because the Earth's orbit is slightly above or slightly below the Earth's penumbra. So we're kind of slightly up or slightly below. We're not lined up in the same plane. Now, when it's all lined up in the same plane like so, well, then we are going to have a solar or a lunar eclipse. But most times it's slightly above or slightly below, so it doesn't line up perfectly. Okay, our last page here, you are to know the moon phases. So we know with our moon phases that we're going to have light on the right. Then that means it is waxing. So wax on, wax off from Karate Kid, right? So the light is growing. And so then we go from new moon where we see nothing because the position when half of the moon is always lit, right? But we don't always see that half. We're standing here looking out this way, but it's this part of the moon right here that's getting the sunlight, and we see this height. So this is a new moon, and then we have waxing crescent. Look at the shape. First quarter, waxing gibbous. Remember, this is less than half. This is exactly half. So less than half. This is exactly half. And this is going to be more than half. And then we get to a full. So then we're on this side here. We're going to be on the waning side is going to be light on the left. So we're going to be turning the light off. Okay, so this is turning the light on. Waxing is light growing. The light is growing. And then with the waning, then it's lessening. There's not as much light. You can see that full, a little bit less, a little bit less, a little bit less to new. A little bit more, a little bit more, a little bit more, full. A little bit less, 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 new, more, full. So here we'd be waxing, 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 full, waning, 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 new. Okay. So you're going to need to be able to identify those moon phases and also understand, name this moon phase. Name the moon phase prior to. So you got to be backing it up in your mind there. Okay, so what happens right prior to a full moon? Well, that's a waxing gibbous. Or you have this. What happens next? You need to be able to identify that this is what happens next. Okay? So nuclear fusion. The sun produces energy through nuclear fusion. Name the two atoms that are combined. So these are the two atoms that make up the sun. Hydrogen, about 75% hydrogen, about 25% helium. Those two combine to release enormous amount of energy through nuclear fusion, and that's how we see the light. That's how we see the electromagnetic spectrum. So here is the spring and neap tide all organized for you. So it occurs when the earth and the moon and the sun form a straight line. Spring, straight. Occur when moon is at a right angle. That would be neap. Whoops. Held on to that a little bit too long. Okay, right angle. So neap, 90. So create the strongest gravitational force, gravitational pull on the ocean. So that's going to be spring. Spring, straight, supersized. Create the weakest gravitational pull. That's going to be on neap. So neap, 90. Not as much. Not as high. Have the largest tidal range. So we're going to have the highest high tides and the lowest low tides. That's going to be our supersize. That's spring. Have the smallest tidal range. So you're going to, when you compare the high tide amount and the low tide amount, it's going to be the smallest because we have the lowest high tide because they are the sun and the moon, they are diminishing each other. They are working against each other, their gravitational pull. So we're going to have our lowest high tide and our highest low tide during a neap tide. Okay? So make sure that you are going back and watching or pausing or doing anything that you need to make sure that you have all the correct answers for your upcoming test. Reach out if you need anything. Have a great day now. Bye-bye.